Good afternoon, everyone. My name is Cameron Benoit, and this is my presentation on pressure relief devices. By definition, pressure relief devices respond to abnormal pressure to prevent overpressure, which safeguards equipment and systems. Applications for pressure relief devices include HVAC systems, all the way to power plants, chemical plants, and other applications. Devices, there are both primary and secondary benefits. Primary benefits of pressure relief devices are that they safeguard against overpressure and safeguard against internal vacuum. The secondary benefits are that it minimizes damage to other system components in the case of abnormal conditions. So getting into the history of pressure relief devices, Dennis Papin developed the earliest pressure relief valve around 1679 for a steam-powered digester. Due to the limitations in weight size, the valves were often undersized, resulting in smaller vent openings than necessary. This sometimes led to explosions when steam pressure increased faster than the vent could release excess pressure, exacerbated by premature pressure release from bouncing movements. Later on in history, direct-acting deadweight pressure relief valves were introduced for early steam locomotives to address Papin's design limitations. Timothy Hackworth pioneered direct-acting spring valves in 1828 on the Royal George locomotive. This design incorporates no adjusting screw and therefore opens at a fixed, preset pressure as controlled by the setting of the compression spring. He employed an arrangement of leaf springs, later replaced by coil springs, to apply direct force to the valve. The spring force could be finely adjusted by manipulating the nuts retaining the leaf springs. Later on down the road, the necessity for such devices became apparent following a series of devastating boiler explosions between 1905 and 1911. This resulted in 1,300 fatalities in the United States alone. From here, the American Society of Engineers introduced its inaugural boiler code in 1915. This code included regulations for the construction and installation of safety valves in response to these incidents. Now moving into the PRD types. There are two main types of PRDs, reclosing and non-reclosing. With reclosing PRDs, they open to react to abnormal conditions of a system, react to relieve excess pressure, and reclose. This prevents further flow of fluid after normal conditions have been restored. Some examples of these PRD types include pressure safety valves and pressure relief valves. Moving into the non-reclosing PRD type, they're designed to remain open after encountering abnormal process conditions. In some cases, a manual means of resetting is provided. If not, the device is made to be disposable. A prime example of this would be a rupture disc. As you can see here, we have an example of the reclosing type of PRD, a pressure safety valve or PSV. This is a safety relief valve that is typically employed in scenarios where excessive back pressure is present. Components, as you can see on the right, of a conventional spring-loaded safety relief valve include an inlet nozzle linked to the vessel or system in need of protection, a movable disc that regulates flow through the nozzle, and a spring determining the position of the disc as shown. The operational principle of PSVs is reliant on force equilibrium. The spring's tension is set to match the force exerted by the inlet fluid on the closed disc when the system pressure aligns with the valve's preset pressure. Once the inlet pressure surpasses the preset pressure, it overcomes the spring force, causing the valve to open. Additional pressure buildup occurs, causing the disc to lift substantially, known as the pop phase. This is why in many cases you will hear to these valves referred to as pop valves. The valve closes once the inlet pressure decreases to a level of below the preset pressure, with this pressure threshold for closure referred to as the closing pressure. The difference between the preset pressure and the closing pressure is termed the blowdown. So we understand pressure safety valves, we can get into the difference between that and a pressure relief valve. In a PSV, the disc obstructing the nozzle possesses a relatively small area and resides within a chamber of a larger diameter. As the pressure surpasses the set point, the stem initiates lifting. Due to the considerable difference in area between the chamber and the portion exposed by the disc, the lifting force is much greater than the spring force, resulting in the complete opening of the valve. This is opposed to the PRV, where the valve opens proportionally to the excess pressure and returns to the closed position when the process pressure returns to normal. Y'all, we're about halfway done. This is probably the most crucial point of the presentation. I can see all of you. Stop scrolling through TikTok reels with your sound off and lock in because we're about to get on with the rest of this presentation. You can see on this chart, we have the relation between pressure and lift for a relief valve and a safety valve. When the set pressure of a PSV is reached, the valve opens almost fully, whereas the PRV opening is proportional to the increase of the system pressure. A relief valve is used to limit pressure in the system, while a safety valve is designed to release excess pressure from the system. Safety valves are used mostly in vapor and steam systems, whereas relief valves are used in liquid systems. As you can see on the two diagrams below, we have both the closed position of a piloted PRV and the open position of a piloted PRV. This is another type of relief valve. With this type of valve, if line pressure is less than the pressure created by the pilot, it will remain seated. When the line pressure increases higher than the pilot pressure, it will open and allow a small amount of fluid to flow through the pilot line into the reservoir. So now we'll be moving to the non-reclosing PRD type portion of this presentation. Rupture discs are employed in scenarios where immediate and complete activation of pressure relief mechanisms are necessary. These devices are installed with the process fluid in contact with the concave side. The rupture disc undergoes expansion as the pressure of the process fluid exceeds the allowable operating pressure. This expansion progresses with rising pressure until the material reaches its tensile strength, leading to its rupture. Assemblies consist of two main components, the first being the disc. A thin metal diaphragm is formed into a spherical shape, ensuring a consistent burst pressure within a predictable tolerance and an extended service life. Secondly, we have the rupture disc holder, which is a flange structure specifically designed to securely hold the rupture disc in place. We have some common rupture disc types. First being conventional rupture discs. After bursting, the dome rupture disc fragments. This type of disc with a flat or angular seat provides satisfactory service if operating pressure is 70% or less of the rated burst pressure. The main advantages of this type of rupture disc are that there are a broad range of applications for gas and liquids, and they're available in various sizes, burst pressures, temperatures, and materials. The second common rupture disc type is the scored tension loaded rupture disc. These discs are designed to open along scored lines, as you can see on the diagram on the right in comparison to the previous one. The scored lines control the opening pattern of this type of disc, which is generally non-fragmenting. This allows up to 85% of operating pressure to disc burst pressure. The main advantages of these discs include not needing vacuum support, and they're available in various sizes and pressures, and they cover a variety of applications. Next, we can get into the knife blade burst method. Currently, reverse acting rupture discs with a knife blade can be used up to 95% of the operating pressure. This method causes rupture discs to open along a predetermined pattern. The knife blades are fixed within the holder, as you can see on the right. Due to the chemical properties of the process flowing through chemical plants and refineries, you can find a PRD combination in service, like as you can see on the right with the rupture disc and PRV. With systems containing corrosive or hazardous substances, there may be concerns regarding potential leakage from relief valves. In this instance, by incorporating a rupture disc upstream, a leak-tight seal can be maintained. With systems containing highly viscous substances, they pose a threat to relief valve clogging over time. By installing a rupture disc upstream, it acts as a barrier, preventing these substances from reaching and potentially clogging the relief valve. As you can see on this slide, we have a few more PRD combinations. Two important ones to take away from this slide are the rupture disc at the outlet of the PSV, as well as parallel installation. The purpose of the rupture disc at the outlet of the PSV is to protect the valve from the atmospheric of downstream fluids. If the relief fluid vented in the common header vented media, it can result in either corrosion or polymerization, as well as a rupture disc would isolate the vented media from the relief valve. In parallel installation, for some applications it is advisable to conduct parallel installation of a safety valve and a rupture disc. In the case of a rapid and unacceptable pressure increase, both units will trigger and perform parallel relief. Next, we move into PRD maintenance and safety. With both reclosing and non-reclosing PRD types, there are inherent concerns with having them installed. The PSV, we have simmering. The blocking disc lifts slightly, allowing the chamber to fill and the process fluid to vent into the discharge pipe. Although this action reduces the pressure, it doesn't fully open the valve. Next, we have the PRV, and we have valve chatter, meaning the pressure in the vessel swings back and forth around the PRV set point with a bigger movement than the dead band allows. Moving on to rupture discs, some of the concerns that we have are during operation, there is a possibility of pitting corrosion, which creates pinholes leading to undetectable leakage. This and or improper seating during installation. Now we have PRDs and HVAC. These devices, as seen in previous presentations, can be found on water heaters, boilers, pressure vessels, and pressurized lines. As you can see on the right, we have a TMP valve on a domestic water heater. One unique application of PRDs and HVAC is the barometric relief damper. These devices consist of thin metal blades or flaps designed to offer a path of minimal resistance for excess air to exit the building whenever indoor pressure exceeds outdoor pressure. Under positive pressure conditions inside of the building, a relief blade prompts the gravity-operated relief dampers to open, facilitating the escape of surplus air. Under negative pressure conditions, the relief blade seals shut to prevent air from entering. The purpose of this device is to prevent the indoor fan from creating excess pressure within the space. Everyone, I'd like to thank y'all for sitting tight during my presentation. Really appreciate y'all. Everyone, here's the quiz. I actually have a bonus question, but it isn't for anyone in the class. It's just to see if Mr. Cliff can identify this song title as well as the artist. So y'all don't really have to pay attention to this, everyone in the class, but all right, here we go.
Kevin Gates, I'm everybody's sworn favorite. People tend to feel I'm Michael Jackson, reincarnated. Satellites never really made love. Alright, satellites never really made love. But she gon' get it right. Emotions probably telling her she could see.
All right, that's all we got. Any guesses?